This is the latest iteration of a device I've been experimenting with, what I've come to call an impulse drive. It is a reactionless drive in the sense that it doesn't need to push against or exchange momentum with its environment in order to move through it, like a car does while traveling along a road or a rocket does while accelerating through the air. The device can move forward using only reaction forces that are internal to the device, and this all works due to the centrifugal forces created by the unbalanced rotating arms. In this slow motion video, we can see the dynamics of the device a bit easier. That when the arms align parallel facing down, the device moves forwards. When they align parallel facing up, this deaccelerates the device down to zero. It's a bit of oscillation because the device isn't perfectly symmetric and balanced, and because there is friction. In an ideal case, the acceleration would be perfectly sinusoidal. The two arms rotate in opposite directions at roughly the same speed, creating roughly the same amount of torque. I say roughly because I literally made this thing out of hot glue and some junk I had lying around. As long as the arms remain in sync, with the same phase but opposite rotation, the vertical components of these centrifugal forces will cancel, and the horizontal components will add. Because the centrifugal force always points straight out from the axis of rotation and is created from a rotation, its projection into the horizontal plane over time will be that of a sinusoidal function. Forces create acceleration, acceleration integrated over time creates velocity, and velocity integrated over time creates displacement. It's a well-known fact that sine of omega t has no average value over its period, but we have to be careful about how we integrate this function if we want to actually understand how this device is operating. The velocity at any point in time is the cumulative integral of the acceleration up to that point. That basically just means that wherever the graph sine of omega t is positive, the thing will accelerate, and wherever the graph is negative, it will decelerate. But if the total acceleration the device experiences throughout time, starting from zero, is accurately modeled by a simple sine omega t function, it will not accelerate backwards. In the absence of friction, it's going to accelerate to its maximum velocity that occurs where sine omega t equals zero, then it's going to decelerate down to zero, then it's going to reaccelerate to its maximum velocity again, then decelerate back to zero. Even though it experiences acceleration that has a negative value, it will never have a negative velocity, which means that the device is going to displace forward. So, to recap, the total force acting on the device over time starting from zero is just sine of omega t, and the device will have no average acceleration, but it will have an average velocity, and it will have an ever-increasing displacement from its original position at time zero. This is because of Newton's laws. If you think that a device operating like this would break Newton's laws, you have no idea what you're talking about. In the future, I plan on doing additional experiments to demonstrate using a similar technique to create a device that produces an average acceleration. In order for a periodic function to have an average value, we basically just require that there is more area of the graph on one side of the zero line than the other. As a simple example for our purposes, we'll focus on trying to make more positive area. The simplest way to give a periodic function average is to just add a constant value to it. But in terms of a physical interpretation, this means the system is no longer closed, because if this graph were representing forces acting on part of an oscillating system, it means that there's a constant force from somewhere acting on that system. So this strategy isn't helpful for creating what we want. A better strategy is to change the width of the regions above and below zero of our periodic function. If all the regions below zero are thinner than the regions above zero, our periodic function will have an average positive value. One example as to how we can achieve that is to modulate the period of our periodic function like this function does. We can see that its peaks are wider than its valleys, and this cumulative integral makes a kind of staircase. Physically, we can interpret this as an oscillation that is asymmetric, like if you were to repeatedly take 2 steps forward and then 1 step back. There are several ways you can physically create an asymmetric oscillation. One of them is through this device in this picture here. I've made other videos going into much more detail about how this thing works, but basically the curves had different curvatures. If they were separate circles and a ball bearing was going around each of them with the same speed, it would do so with a different period for each curve. So by joining the two curves together, we have effectively mixed those two frequencies into an asymmetric periodic function. But what's great about our example function is that it's explicit and continuous, which means we can apply Fourier analysis to it and approximate it with the superposition of a bunch of other simpler periodic functions. This means that we don't actually need to build some kind of exotic physical embodiment of a periodic function with an average value. We can approximate that behavior with the physical embodiments of a bunch of carefully tuned symmetric periodic functions that don't have average values. This is an example of the mathematical results of doing so up to the 24th harmonic. 24 harmonics is a lot, but we can see that not all of the AI and BI coefficients computed are as significant as others. The second last graph is the approximation of our original function with only 6 of the most significant terms, and furthermore without the average value a0. The last graph is the cumulative integration of the previous one. So we can see from this example that we can get a close enough approximation using our symmetric periodic functions to the original asymmetric periodic function such that we recover the desired property of its average value without actually adding an average value into the approximation. And this doesn't take that many harmonics to do so. Also, that it actually is possible to design a closed system that can displace itself by vibrating forward due solely to internal motion. Because the secret sauce to this is effectively just a difference in timing between subsystems, I've come to call this an impulse drive. Thank you for watching.